In this video, we'll discuss creating valid arguments using logical inference and equivalences. But first, let's talk about what we mean by constructing valid arguments. So we'll say an argument is a sequence of statements starting from a set of premises or assumptions that uses steps of reasoning from equivalences or inferences to reach some conclusion. We say that an argument is valid if and only if the conclusion can be shown true using steps of reasoning if the premises are true. An argument is sound if and only if the conclusion can be shown true using steps of reasoning and the premises are true. So let's see what we mean by these definitions, and we're going to express the statements for valid and sound arguments in propositional logic. So let P be this proposition that an argument is valid, S that the argument is sound, R the premises are true, and Q the conclusion can be shown true using reasoning, steps of reasoning such as inference and equivalences. But we'll just call it the conclusion can be shown true for Q. So we say that an argument is valid if and only if. So we're going to now translate the definition that we had for validity. So valid is going to be an argument is valid, P, if and only if the conclusion can be shown true using steps of reasoning if the premises are true. So that means if the premises are true, then the conclusion can be shown true. So that's R implies Q. Now sound, we say that an argument is a sound, so we'll call this soundness. And this we can call validity. Argument is sound if and only if the conclusion can be shown true using steps of reasoning and the premises are true. So that's R and Q. So that's the main difference between validity and soundness, that an argument is sound if and only if the premises are indeed true and you can show that the conclusion is true, whereas validity is when if the premises are true, then you can show that the conclusion is true. So it's a slight difference, but we just use this as a way also to express validity and soundness in terms of propositional logic. But the most important takeaway that we're going to have is how can we actually start using equivalences and inference in order to show conclusions, logical conclusions. So let's jump into this, and I just wanted to talk about the rules of inference. So it's not so important to know what they're called, but it is important to know how to use them. So it's completely fine if you don't know modus ponens or modus tollens or hypothetical syllogism. That's completely fine. But it is important to understand how you can apply these rules of inference. And sometimes you may have noticed that I had been doing this in different parts of the previous videos. Okay, so modus ponens, that says if P is true and P implies Q, then Q is true. So that's if the premise holds and P implies Q, then the conclusion. So let's look at a concrete example. It is raining, and if it is raining, you carry an umbrella, then you carry an umbrella. That's an example of modus ponens. Now, modus tollens is essentially using the contrapositive. So, modus tollens says if P implies Q and not Q, then not P. So, for an example, if it is raining, you carry an umbrella, and you are not carrying an umbrella, then it is not raining. Now, hypothetical syllogism is a way to use inference with two different implications. So if P implies Q and Q implies R, then P implies R. As an example, if it is sunny, then you go to the beach. And if you go to the beach, you swim in the ocean. Then, if it is sunny, you swim in the ocean. Other rules of inferences are dealing with disjunctions and conjunctions. So disjunctive syllogism is P or Q, and not P, then Q. So the farmer harvests ripe kale today, or the farmer eats winter squash. And the farmer did not harvest any kale, so the farmer eats squash. So if P or Q is true, and you know that P is false, so not P, then Q must be true. Now, addition, P, then P or Q. So basically, if you know that P occurs, then you can add another proposition to that, then P or Q, and you'll know that P or Q is also true. So as an example, the farmer harvests kale, then the farmer harvests kale, or the farmer eats winter squash. It's an example of addition. Now, for simplification, is if you know P and Q is true, then P is true. So the farmer harvests kale today, and the farmer eats winter squash. Then the farmer harvests kale today. In conjunction, if we know that P occurs and Q occurs, then P and Q occurs. The farmer harvests kale today. The farmer eats squash today. Therefore, the farmer harvests kale and eats squash today. Now, for resolution, we have two disjunctions, and we can deduce a third disjunction. So, if P or Q is true, and not P or R is true, then Q or R is true. So, in that case, we know that either P or not P has to be true, so that means either Q or R would have to be true. And we know that it couldn't be both P and its negation being true, so that's where resolution comes from. The farmer harvests kale today, or the farmer eats squash today. The farmer does not harvest kale today, or the farmer eats oranges today. Then the farmer eats squash or oranges today. So resolution comes from the disjunction involving P and its negation. So if both of those disjunctions are true, then we know that Q or R must be true, because both P and its negation cannot be true simultaneously. Okay, now one important detail is that these rules of inferences are actually tautologies, and we're going to show that now that a rule of inference is a tautology. In particular, we're going to show that modus ponens is a tautology. That means these rules of inference are always true, and if you're in doubt, you can actually verify this using a truth table. Right now, I will show that modus ponens is a tautology, but I will use equivalences to reinforce equivalences. But I want to reassure you that you could also do this exercise using a truth table. So what do I mean by modus ponens being a tautology? I mean that the statement of modus ponens is always true. So what is the actual statement? So now we said before that modus ponens is P, and P implies Q, then Q. So let me write this in terms of propositional logic. So what it actually means is P and P P implies Q implies Q is equivalent to true. That's what we mean by a tautology. It means it's always true. And you'll notice that when I wrote the modus ponens more formally as just a proposition, that I was careful in terms of specifying the implication. So now let's just show that this proposition is always true. So I'll start off. So we have P, and P implies Q implies Q. And now the first thing I'm going to do is I'm going to use the equivalence of the implication for this implication right here. So I'm going to have P and not P or Q implies Q. So that's just using the equivalence of an implication. And by that I mean that P implies Q is equivalent to not P or Q. Okay, now let's see what I can do. Well, I can distribute P right here, use the distributive law right here. So I'm going to have P and not P, or P and Q implies Q, and that is the distributive law. Okay, now you'll notice that P and not P is one of the clauses, so I know that that is a contradiction. So I'm going to have false by the contradiction. So P and Q implies Q. That's a contradiction. And that is because I know that a statement and its negation cannot be true at the same time. And then whenever I have false or another proposition in a disjunction, I know that the truth assignment of that disjunction, that or, is just going to be determined by the remaining clause that isn't false. So that is what we mean by identity. So here is where I notice the identity, and because of that I know that this false or P and Q can just become P and Q, and that is just using identity right there. And in that case, the identity is false, or any proposition is just going to be that proposition. Now we can use the equivalence with an implication again. So we have to negate the premise. So here I'm going to negate P and Q, or Q. So that's implication again. And I can use De Morgan's law on that negation. So that's going to be not P or not Q, and then we have or Q. That is just applying De Morgan's law. And finally, we can apply associativity also at the same time. So, and by that I mean it doesn't matter how I perform the disjunction, and they're all disjunctions. So I can do not P or not Q, or I can do not Q or Q first. So that's going to be the associativity also. Okay. Now you'll notice that I have not Q or Q, and either a statement or its negation must be true right here. So this, you'll notice, is a tautology. So that's true, that's a tautology. And then whenever I have not P or true, then I know that disjunction is going to be true because of domination, because once you have a true term in a disjunction, you know it's going to be true. So we've just shown that modus ponens is indeed a tautology, so it's always true. And you can also verify this using a truth table if you would like as well. Now we'll apply the rules of inference and equivalences in order to construct a valid argument through an example. Dr. Doe is worried about patient A's cholesterol and is trying to construct a treatment plan. Dr. Doe has the following premises. First, if patient A has lower cholesterol, patient A will be healthier. Second, if patient A loses weight, patient A will have lower cholesterol. Third, if patient A does not lose weight, patient A eats at In-N-Out every day. And fourth, if patient A no longer eats at In-N-Out every day. And the last is just a statement. Patient A does not eat at In-N-Out every day. And for those of you not from Southern California, In-N-Out is a very popular fast food restaurant here. And the conclusion is that patient A will be healthier. Now, how could we show that Dr. Doe's plan is valid? And we're assuming that the premises, those are the first four statements, are valid. So when we want to check if an argument is valid, the first thing we have to do is we have to translate each of the premises and the conclusion into propositional logic. And when we do that, we first have to decide what our atomic propositions and the propositional variables will be. So let's just do that. We have P, the proposition patient A has lower cholesterol. Q, that patient A is healthier. S, patient A loses weight. And finally T, that patient A eats at In-N-Out every day. Now our premises will be patient A has lower cholesterol, then patient A will be healthier. Well, that's P implies Q is the first premise. Then if patient A loses weight, patient A will have lower cholesterol, so that's S implies P, our second premise. Then if patient A does not lose weight, so we have to negate S, so that's not S, then patient A eats at In-N-Out every day, that's T. And finally, our fourth premise is patient A no longer eats at In-N-Out every day, so that's not T. And our conclusion, Q, is that patient A will be healthier. That's our conclusion. So we've translated all of our premises and our conclusion into propositional logic, and now we want to see if there's any all of the premises are true for this exercise every day. So that's not T. And our conclusion, Q, is that patient A will be healthier. That's our conclusion. So we've translated all of our premises and our conclusion into propositional logic, and now we want to see if there's any inference or equivalences that we can use to show that the premises do indeed lead to the conclusion. Okay. Let's apply the rules of inference to see if we can reach the conclusion, and we are assuming that all of the premises are true for this exercise. So since patient A does not eat out every day, so that is not T, that's premise 4, we can use premise 3 and modus tollens. So premise 3 is that not S implies T, and that is that if patient A does not lose weight, patient A eats at In-N-Out every day. So modus tollens is that not S implies T, and we're told not T, then what we can infer is not S. And this comes from the contrapositive. And what we mean by that is if we negate the conclusion, so that is not T, that means patient A no longer eats an In-N-Out every day, then we can negate the premise. And here, when we negate the premise, we have to take not S and negate it. And that means that we would indeed have S. So let me do that. Not S, which, because of double negation, that's double negation, is equivalent to S. So here, by modus tollens, we can infer S, and S is that patient A loses weight. Now, by premise 1 and premise 2 and hypothetical syllogism, we can combine these two implications. So premise 1 and premise 2 is, so premise 1 is P implies Q, and premise 2 is S implies P. But the order that we'll use them for a hypothetical syllogism is S implies P and P implies Q, then S implies Q. And so what we mean by that then is that S implies Q just means that if patient A loses weight, patient A will be healthier. Now, since we already inferred S, we can apply modus ponens with our next inference that we have. So these are the two inferences we're going to use. So since we have S and we just inferred that S implies Q, then by modus ponens we can infer that Q is holds. And by Q we mean that patient A will be healthier. And that's the conclusion. So here is how we can use inference and also equivalences in order to show how we can use premises to reach a conclusion.